Screencast number 8. We're going to try to go through this quickly and make this the concluding one for this chapter. So this is chapter 21, New Renewable Energy Alternatives. So one of the things that we want to talk about is ground source heat pumps. And these are in about 600,000 homes in the United States. And because the ground absorbs, the soil on the ground absorbs heat more slowly, it retains that heat and it doesn't change temperature at a certain point far below the ground. So we can put these geothermal pumps in our homes where we run the pipes down and we have water that has antifreeze in it, and it picks up the temperature of the underground, and it doesn't have to be raised temperature-wise too much. And we bring it up into our houses and it can heat our homes. So like the average temperature of the ground is like 60 degrees at certain areas underground. So you're bringing that up and you don't have to raise the temperature too much higher, don't have to expend too much energy in order to change the temperature. What also happens is, if you think in the summertime, if it stays at 60 degrees and you bring this cool water in, it's going to help cool your homes. So when you use these ground source heat pumps for the geothermal energy, the heat space is 50 to 70% more efficient. It cools them 20 to 40% more efficiently, and it actually reduces electric cost 25 to 60% and can reduce emissions up to 70%. So here is a diagram of a house that has the ground source heat pumps that are put underneath the ground, and you can see how it runs through the whole bottom of the home. The network of pipes is filled with water and antifreeze, and the soil is cooler than the air in the summer and it's warmer than the air in the winter. So by running the fluid through the house and the ground systems, they adjust the temperatures inside the home. Okay, so let's move on to ocean energy sources, and there's multiple sources from tides, waves, and currents, and we know that this is a form of kinetic energy. So one of the things that we're doing is we're trying to harness the motion of waves and convert that into mechanical energy. So this is wave energy. There have been a few adequately new tested facilities that are offshore. They involve floating devices that move up and down with the waves. The one that is on the cover of our textbook that you see is one of these devices. This is made by a Scottish company, Palamis, which means snake or snake-like, sea snake. And these are snake-like wave energy converters that you see on the front of our cover. There's variations on this jointed columnar design, and they have deployed several of these in parts of the world. The machinery and hydraulic fluids inside the float columns are used with the wave motion to generate electricity, which is then transmitted to shore by undersea cables. The wave energy is greatest in deep ocean sites, so there's more waves in the deep ocean, but transmitting electricity to the shore, as you can imagine, would be very expensive. There have been some designs that work along the coastlines, and onshore we can funnel the waves from large areas into natural tunnels, and this would work similar to the way that we do our hydraulic dams. There's other coastal designs that relies on the falling of the waves to push air into chambers that turn a turbine. The first commercially operating wave energy facility was built in 2011 in Spain, and it uses technology that has been tested for a decade in Scotland, and it demonstrates that we also have demonstration projects that exist in Europe, Japan, and Oregon. We are developing ways of harnessing energy from tides. The rise and falls of the tides happen twice a day, and it moves a very large amount of water. So the differences in height between low tide and high tide are especially great along narrow bays. So Alaska's Cook Inlet and the Bay of Fundy between New Brunswick and Nova Scotia are two examples. These locations are best for harnessing tidal energy because they accomplish this by erecting dams across the outlet and tidal basins. The incoming tide flow through the sluice gates is then trapped behind them, and as the outgoing tide passes through the gates, it turns the turbine and it generates the electricity. So this is what the machine would look like. The air inside is alternately compressed and decompressed, and it creates an airflow that rotates the turbines, and that generates the electricity. There are smaller facilities that use this in Canada and China and Russia and the United Kingdom. The U.S. first tidal station began operating in 2012 in Maine, and one is scheduled to be built in New York City's East River starting on 2013. These tidal stations release fewer or no pollutants, but they can affect ecology in estuaries and tidal basins. There's 5 more tidal stations that are planned in South Korea, but they've been delayed in the wake of concerns of other environmental impacts. And then the third way to harness marine kinetic energy is to use the motion of ocean currents, such as the Gulf Stream. And we have devices underwater in the Gulf Stream that powers turbine devices that have been erected to gain energy from. Okay, so here's other examples of how the turbines could work. So this is the way that we could harness tidal energy, and we use these bulb turbines with the outgoing tide. At low tide, the water is out, and when it comes in, the water spins the turbines and generates the electricity. And this technology is used at the new Shiwa Lake tidal generating station, which is in South Korea, and that's the one that's pictured above. Okay, another way is looking at the thermal energy, which is in the ocean. As you know, the ocean water can absorb solar radiation, and it can heat the content of about 250 billion barrels of oil, or equivalent to, enough to provide 20,000 times the electricity used daily in the United States. So the ocean's sun-warmed surface is warmer than its deep water. This is called ocean thermal energy conversion, and it's based on gradient temperature. It is a closed cycle approach where the warm surface water is piped into a facility to evaporate chemicals such as ammonia that boil at low temperatures, and then these evaporated gases spin turbines to generate electricity. The cold water is piped up from the ocean depths, and it then condenses the gases so that they can be reused. And this is referred to as an open cycle approach because the warm surface water is evaporated in a vacuum, and the steam then turns the turbines, and then it's condensed in cold water. Because the ocean water loses salts as it evaporates, the water can be recovered, condensed, and sold as desalinized fresh water for drinking or agriculture. So the OTEC research has been conducted in Hawaii and elsewhere, but the costs still remain very high, so no facility operates commercially yet. So the last thing that we want to just kind of talk about is hydrogen. And this is a very renewable energy resource because hydrogen is everywhere. It cannot conduct electricity, but it can store energy in large amounts. So there's a lot of people that want to use hydrogen because it would prove a clean, safe, and efficient energy system. Um, it could be used in a system where electricity is generated from some intermittent renewable sources like wind or solar energy, and then they could use that to produce the hydrogen. What we can do is we can create fuel cells like hydrogen batteries from the hydrogen that could then use the hydrogen to produce electric energy to power vehicles, computers, cell phones, heating, and other applications. NASA has been using the fuel cell technology since the 1960s. Basing an energy system on hydrogen could alleviate our dependence on our foreign fuels. It could help fight climate change. So governments are funding research in the hydrogen and fuel cell technology. It's still very expensive to do. We're trying to launch a network of hydrogen filling stations so that we could have hydrogen cars. But again, the costs are really high. So in this system, this is how a hydrogen fuel drives electricity, and they generate it in a fuel cell, creating water as a waste product. So you're going to see that atoms of hydrogen, here's our atoms of hydrogen, are going to be split. They're going to be split into protons and electrons. Remember, hydrogen doesn't have any neutrons. And this is going to pass through a proton exchange membrane. And then the electrons will then move from the negative electrode to the positive electrode. Here's our electrodes here. And this is going to create a current of electricity. And the protons and electrons can then combine with oxygen that you see here, and we can get water molecules that are produced. Here's another example with buses. Hydrogen gas does not tend to exist freely on Earth. Instead, hydrogen atoms bind to other molecules, and they become incorporated in everything from water to organic molecules. So scientists are studying several ways of producing hydrogen in a process called electrolysis. And this is where electricity is input to split the hydrogen atoms, like you see in this fuel cell, and it produces pure hydrogen. The environmental impact of this production will also depend on the source material for the hydrogen. Water and hydrogen can be obtained from biomass and from fossil fuels. So we can also use this to reduce or extract from methane gas as a possibility. And there's the methane example. So, of course, there's the water example that we were talking about. We can take it and put it together to get the water. So there's some benefits. There's a massive cost in developing the infrastructure. There's a lot of research that has to go into studying the leakage because it could deplete the ozone. We'll never run out of hydrogen. It's always there. It's clean and not non-toxic. It produces fewer greenhouse gases and pollutants. If it's kept under pressure, it's no more dangerous than gasoline in tanks. Cells are typically anywhere from 35 to 70% energy efficient, and the fuel cells are silent and non-polluting, and they don't need to be recharged. I'm going to ask you to finish reading the conclusion for this, and we are done chapter 21.